All right, we're on chapter 25 now. This is really just kind of an extension of chapter 26. Of chapter 24, which was our introduction to other galaxies, sometimes called alien galaxies. It just means they're outside of our galaxy, the Milky Way. So you remember we had the three basic types of galaxies: spiral, elliptical, and irregular. And then we also divided galaxies into just normal galaxies and active galaxies. Active galaxies, there were the Seyfert, the radio, and also quasars. All right, and so we're going to examine this in a little bit more detail, and in fact relate it to the structure. And so this is really the thing that I'm talking about is the large scale structure of the universe, and also the evolution of galaxies. All right, so these are the subjects that we're going to cover in chapter 25. Dark matter. So we're going to find out that it's not just the Milky Way that has dark matter. This seems to be everywhere, surrounding all other galaxies, all types of galaxies. It seems that in the very early universe, especially about 10 billion years ago, there was a great deal of galactic collisions. There's still galactic collisions, but more often, they occurred much more often in the past, as we're going to see. So galactic formation and evolution, that's what I was mentioning. We're going to see that some of these active galaxies, they don't stay active forever. When they start to lose their fuel supply, or this fuel supply runs low, they're not what we would consider active anymore. And then what do they become? So we'll go into that. A little bit about the Sloan Digital Survey. What do supermassive black holes at the centers of galaxies have to do with galaxies, actually? And that's actually a really good question about the evolution of galactic evolution. And then again, the last thing is the large scale structure. All right, so here's something that we that we look at, which is called the rotation curves. So this is what originally told us that the Milky Way was surrounded by this material, something. Well, we don't know even if it's material. We just know that there's something there gravitationally interacting with the stars in the outer parts of the Milky Way. And so we look at other galaxies, and we see the same kind of thing. These same what are called rotation curves. So if you look at the rotation speed versus distance from the center, you would so if all the mass is the mass that's observed in a particular galaxy, this curve, after let's say about 20 kiloparsecs or so, it should start to drop down. But there's something out there that's causing the stars really, really far out to rotate just as fast, if not a little bit faster. All right, so that, of course, is what we've called dark matter. All right. So here's another situation: is we can actually look at let's see, another way to measure the average mass of galaxies in a cluster is to calculate how much mass requires to keep the cluster gravitationally bound. Right? If you look at a cluster of galaxies, and they're all moving in different directions, how much, are they moving fast enough to escape? Like, let's say from some point at the center of a cluster, you can actually calculate, what would be the escape speed, and then you look and you see that these things are not escaping from a particular cluster, and so you can actually calculate the mass of the overall cluster. All right. Oops. Oh, already do this? Let's see. Sorry, I was going in the wrong direction. All right, so we just did that. All right. So galaxy mass measurements to show the galaxies need. So just for the average galaxy, let's say, they need anywhere from 3 to 10 times more mass than can be explained. It can be measured via radiation. In other words, something that is emitting or reflecting, or some kind of radiation coming from these galaxies. So the amount of mass required to keep the galaxies together is, or to explain the rotation curves, is anywhere from 3 to 10 times more mass than we observe, right? And so there's this, this is for every galaxy, not just the Milky Way, okay? And so there is all this this dark matter out there, and then it's even more for galactic clusters, right? So again, if you look at these clusters, let me get my mouse here. So for a cluster of galaxies to remain bound to the cluster, right, gravitationally bound to the cluster, we need anywhere from 10 to 100 times more mass than is observable. Like if you add up all the mass of all the galaxies in that particular cluster, there's not enough to keep the galaxies from escaping. All right, so you need more mass, and they're not, right. They're not escaping. We can measure their velocities. I'm talking about the velocity of the overall galaxy. And you see that it's not enough to reach, to escape from the cluster that, and so there's anywhere from 10 to 100 times more mass depending on the cluster that is unexplained, that is not visible in any form of electromagnetic radiation. That matter is there gravitationally, or whatever it is there gravitationally, and that's what we call dark matter. So there's a lot more dark matter. There's evidence for so this is it turns out we find dust, sorry, not dust, dark matter in clusters. All right, so this is evidence. So we find, like, for example, there's this super hot gas that is found. I think this particular one was found. I forget which one it was. Anyhow, we of course can measure the temperature of the gas because it's emitting radiation. It's black body radiation. So we find that, let's say it's 10 million Kelvin. And that dust is the thickest at the center of the cluster, but to keep that much dust, or to keep dust at that temperature from escaping, right? Because remember, temperature is really a measurement of the average velocity. We've done several calculations like that before, and so. If that's the temperature of this dust within this cluster, then that should be more than enough for that dust to escape. And of course, it hasn't, because we're still observing it, and so there must be more mass within the cluster to keep that. That is dark matter, of course, that keeps that dust from escaping. Let's see. So this, of course, is a radio galaxy, also known as a burster. We learned about that. Remember, these are active galaxies, and they are almost always associated with elliptical galaxies. Just to let you know. Let's see. So this is an example of this particular galaxy is moving, let's say, downward, right? So this is towards the bottom of the picture, and there's something that's sweeping the lobes in the opposite direction, right? And so that's this intra-cluster gas, right? So this is gas within the cluster itself that's pushing. As the gas interacts with the lobes, it pushes these lobes back. It's just like a boat passing through water, right? The bow passes through the waves, and then the evidence of the boat is swept past, behind the boat, right, as the boat plows through the water. All right, so that's an example. So what is this gas? I mean, where did it come from? I mean, you have this gas that's, and there seems to be a good deal of it here. And so where did it come from? We think that this was the original primordial gas, which, in other words, it's hydrogen and helium, right? Roughly 75% hydrogen, 25% helium. Although, just to let you know, that we do find some heavier elements within this gas inside of these clusters. Right. So this is this is gas that's not associated with a particular galaxy. It's just within the cluster of galaxies. But of course, there's just a small amount of like carbon and things like that, which just indicates that, as galactic evolution takes place, as stars die and they either explode or they lose some of the mass due to planetary nebula, that some of that matter will even escape the galaxies and go out into get mixed up, in other words, with the primordial gas, and that's what we're seeing. So it turns out, of course, this is not nearly enough, as it says here. Of the gas, in particular, is not nearly enough to account for the gravity, right? For the gravity that's observed. All right, so let's see. So this is this is a huge idea. And especially in the early parts of the universe, about 10 billion years ago, this was a much more frequent occurrence, although it is still going on. It is what we call galactic collisions. So we're going to look into these things. There's actually what's called galactic mergers, and then there's sometimes it's called galactic cannibalism. Cannibalism is more of like a large galaxy feeding off of it's not really feeding, obviously, but it's absorbing a smaller galaxy. Mergers are when two galaxies that are about the same size come together and form a larger galaxy. This is an example. This is sometimes called the cartwheel galaxy. Astronomers, sometimes have a little bit of a sense of humor about these things, or they're just looking at something and just describing it. So here's another galactic collision that's taking place. This is with two spiral galaxies that are coming together, and as long as the spirals are as long as one of the galaxies is smaller than the other, significantly smaller, and in fact we're still trying to figure out exactly how small the second galaxy has to be for the original galaxy to maintain that spiral structure. All right, so just to give a little bit of this away, and this is going to be a couple of slides from now. When the two galaxies, let's say it's two spirals that collide with each other, we actually think that the spiral structure will not survive if they're the same, if they're roughly the same size. That what comes from that is an elliptical galaxy. All right, so. So one more evidence of galactic collisions is what we call starburst galaxies. So these are galaxies where two galaxies have come together, and we view that, and of course we see tremendous